Okay, so our first talk is relating to fact verification.
Good afternoon, everyone. My name is James Thorne, and I'm going to be presenting on recent work on adversarial attacks against fact verification systems. And a key part of this is how we evaluate the quality of adversarial attacks and how we can compare those given the correctness of the instances being generated by the adversarial attacks. So this formed the basis of a recent shared task. The FIVA shared task was hosted at the FIVA workshop on Sunday, the first day of this conference. And I encourage you to check out the website fiva.ai if you're interested in that. So I'm going to start by introducing what fact verification is. So this is a task where we want to predict whether a claim is true or false given evidence. So the format of this task is in two stages. Firstly, given the model is provided only with a claim, and they must identify evidence from Wikipedia at a sentence level. And then what they must do once they have these sentences is predict whether the claim is supported or refuted given the sentences that have been returned, or return not enough information if there's no evidence retrieved from Wikipedia to support this claim. So in the example about the Rodney King riots, we see in the first sentence, we're retrieving a sentence defining what the tasks are and what the riots are and where they occurred. And then there's a multi-hop reasoning step where we retrieve evidence about LA County in order to fully answer whether the claim, or to fully support the claim. And so the FIVA task is scored with the FIVA score, which is a combination of both the evidence retrieval and the labeling. And a key difference between this and other tasks is that it's necessary to return the correct evidence and have the correct label in order to get a point. And so if you apply the correct label without returning the correct evidence, then no point is awarded. So why would we want to attack FIVA? Well, firstly, attacking models provides insights into limitations of the models which are being deployed. But also, these models are trained in a supervised environment on data which is written by human annotators. So this further allows us to probe the limitations and the biases within the data set. And if you're aware, there's a session after this in 7D where there's a couple of papers looking at some of the limitations in these data sets. And this kind of follows on from work which was previously published at NACL 18 on kind of limitations within natural language inference data sets. And furthermore, given fact verification and the recent work on fake news and misinformation, it has potentially sensitive applications if we were to deploy this to the wild. And it's important and kind of critical to understand what the limitations of the models are when they're exposed to data from outside of the training distribution, but also whether there's any blind spots which people could use to game the systems and exploit it for their own purposes. So in this case, we decide to use adversarial attacks as a way of probing the models and looking for these limitations. So for those of you who aren't aware, the adversarial attacks kind of originates from the field of, popularized in the field of computer vision. And I'm sure you may have seen this example before. It's kind of the canonical one, where on the left you have an image of a panda. And on the far right, you have a perturbed image, which to humans is imperceptibly different. However, there's an additional perturbation in the center, which is deliberately designed to induce a classification error. And so on the left, the model would have predicted a panda with a certain confidence. And then after the addition of this, perturbations which humans can't necessarily see or determine, the model predicts a gibbon with a high degree of confidence. So in attacking natural language processing systems, we want to do similar things. We want to take instances from a data set and make perturbations or changes to these models. And an easy way to do that is with human annotation, taking a claim and manually editing this. But that doesn't really scale well to large sizes of data sets. So it's typically it's become more common to do automated methods of generating these adversarial attacks, but it's actually quite difficult to do that for a number of reasons. So firstly, there's a discrete symbol space in language. The addition of a word is perceptible, and so we can't immediately compare to the image classification example. Also, it's very easy to add a word which would unintentionally change the semantics. So if I was to add a negator or a quantifier, the semantics of the claim would change, and that may no longer be able to be entailed from the evidence which we had originally had in the data set. And firstly, and secondly, there's also limitations in the adversarial methods, and the authors of several recent state-of-the-art methods have each revealed that the instances generated by the automated methods of generating the adversarial attacks are not always grammatically correct and may not semantically follow from the instances that they were generated from. So this means that there's a chance that the label of the instance we're attacking may be wrong given the content of the claim. And so what we want to do is evaluate models under adversarial attack, accounting for whether the instances are correct or not. So it's not only sufficient to induce an error in the system. We want the error to be because of a limitation in the model or the data that the model is trained on that we're exposing, not because the adversarial attack instance is incorrectly labeled. And so we propose two metrics which were part of the shared task for Fever. Potency, which measures the quality of the adversarial attack. So that's like error rate, accounting for how correct the adversarial attacks are. And then resilience as well, which measures the resilience to, or how systems perform under adversarial attack, also accounting for the correctness rate of the instances that it's being tested with. So let's have a look at these metrics. So both of these metrics where we want to get a higher score if it's better. So for potency, we look at the difference in classification from a perfect system. So you'll see on the equation there's a 1 minus f, and this f in our evaluation is fever score, but that can be exchanged with any other measure you're using, such as f1 or accuracy. And what we do is take an average over all systems that you're evaluating, weighted by how correct the instances are. And you can estimate the correctness rate by sampling or some other way of generating a scalar for this. And so given a set of systems you want to evaluate your adversarial attack on, we are effectively just averaging over the reduction from a perfect score. And the complement to this is the system resilience. So again, our intuition is that better systems would have a higher score, but then for evaluation, we want the adversaries which are generating higher quality attacks to be weighted more than adversaries which are generating nonsense when we're evaluating our systems. And so we have a weighted average, again, with the correctness rate of the adversary which we're exposing the system to. So then comes the point where we do an empirical evaluation, and we look at 6 fact verification systems and 3 methods of generating adversarial attacks. So we take 4 state-of-the-art systems, and these were the highest ranked systems from the first fact extraction and verification shared task. And then we also have 2 simpler baseline systems, which consist of a TF-IDF-based document retrieval system and a simple NLI classifier. And we're exposing these systems to 3 classes of adversarial attacks. One is a state-of-the-art attack called SEERS, which is a model-informed attack. So basically, this is probing the model and seeing how that behaves. We have a paraphrase-based attack, which is lexically informed. And we also do rule-based attacks based on observations on the data set. So I'll come on to these in the subsequent slide. But then for the purposes of evaluation, we also sample a balanced test set of 1,000 instances from each of these adversaries. And to estimate the correctness rates for each of these adversaries, we take a sample of 100 instances which were blindly annotated by external annotators. So starting from the rule-based attacks, these were manually constructed regular expressions based on observations in the dataset. So the claims in the Fever dataset were manually generated by human annotators, and some of these annotators use common patterns when generating their claims. So we looked at the most commonly occurring bigrams within the dataset, and the least commonly occurring bigrams. And what we did was we rewrote the most common ones with kind of rare expressions using templates such as the one on the screen. So there were 63 of those in total, and they were performing different operations, including making label-altering negations, changing the voice from active to passive, and so on. The second class of adversarial attacks were the automated ones. So we took Sears, which was it's a state-of-the-art method from Ribeiro et al. And what this does is paraphrases each claim and then runs this on one model and then looks at what kind of paraphrases induce errors and apply those paraphrases to all matching instances within the data set. And then the final method was a WordNet-based paraphrasing method, where we firstly replace tokens within the sentence with their synonyms, and then run that through a paraphrasing model as well. And replacing the tokens with synonyms was a way of encouraging diversity in the instances being generated. So all the systems we evaluated the adversarial attacks on follow a common sort of pipeline architecture, which loosely consists of evidence retrieval and a natural language inference component. And it's worth noting as well that 3 of these models we evaluated were eSIM variants, and one was a transformer variant as well. And the automated attacks on the Sears or using the Sears method, we're attacking an eSIM model. So that will be reflected in the upcoming slides. So firstly, let's look at attack potency and what do we understand from this. So the highest, the attack which induced the most number of errors was the paraphrase-based attack. However, once we consider how correct the instances are generated from this method, this ranks last in our approach. So under our manual annotation, the paraphrase-based adversary was only correct 1/3 of the time, which means that under our score of the potency, it was the worst. Whereas the rule-based attack, which were generated by humans, were correct most of the time, and had the highest potency in this evaluation we performed. Let's move on to system resilience. And we firstly indicate the system scores on the first fact extraction and verification shared task in the Fever score column. And we find that and then we evaluate the systems according to resilience. So this is using different data and the data we generated with the adversarial attacks. We find that the systems are largely correlated and remain ranked in the same position, although the transformer model moves from 4th place to 1st place, possibly due to the fact that the adversarial attacks, or one of the classes of adversarial attacks, were against eSIM-based models rather than transformer architectures. And then recall that the systems are a pipeline of evidence retrieval components and a natural language inference classifiers. We found that the evidence retrieval part was less well affected than the NLI, with the exception of the transformer model, which modeled the task of evidence selection as a binary classification. So what did we do in this paper? We firstly kind of motivated the need to perform adversarial attacks against fact extraction and verification systems, but realized that generating attacks against NLP systems is challenging due to the discrete symbol space. So not all the methods generated correct instances, so we introduced two new metrics, potency and resilience, which account for the correctness of adversarial instances. And we showed their application to a large number of models and methods of generating adversarial instances, which formed the basis of the second Fever shared task. So if you're interested in this, you can find out more on our website or following us on Twitter. Thank you very much, and I'll take questions.
So any questions from the audience?
Okay, thank you. Interesting talk. So what is your effective defense mechanisms?
So there's many ways to defend against fact-checking models. Some of them are already well established. So you can do adversarial training and incorporating the instances as a fine-tuning mechanism. But then Tuhin, who was the previous presenter, had a paper at our workshop where they performed observations on the types of instances and showed that systems weren't capable of doing multi-hop temporal reasoning, and so introduced an additional component to their pipeline, which made the system more resilient to that.
Any other question? So you define two metrics here, right? Mm-hmm. Were there any other metrics defined by some other work? Have you actually compared your metrics with others?
So most of the other works, the works we identified perform a manual evaluation of some of the instances as well. And we find that they say how often the instances were correct, but this wasn't incorporated into their scoring methods, which was the motivation to do this. I'm not aware of any other metrics which incorporate that yet in the NLP domain.
Is there any further question on this work? If not, let's thank the speaker again.